All right, here are solutions for quiz 7 for Math 252. Two different questions on this quiz. First one dealing with improper integrals, 510 in your book. And the second one dealing with area bounded by curves, so 6.1 in your book. But this first one, this improper integral problem, the way you know it's an improper integral is the function that's in the integrand here, the natural log of x, is undefined on one of the bounds of integration. Natural log of e, that's fine, but natural log of 0, that's undefined. So what that means is we can't just use the evaluation theorem to figure out this definite integral. That's what I was getting at in this first hint here. What you instead have to do is change the lower bound of integration here into a constant and then take the limit as that constant approaches this number 0. What I'm saying is we can rewrite this integral in this form. And technically a should be approaching 0 from the positive side, because if you approach from the negative side, the natural log of a negative number is undefined. But it's not a big deal if you left off that plus, but technically there should be a little plus here. So this is the thing I'm going to need to evaluate. And to evaluate this thing, well, because I changed my bounds of integration, now I can use the evaluation theorem. But to use the evaluation theorem, I'm going to need to know the antiderivative of this guy. So maybe that's work I should do off to this side. That's what this second note is getting at here. It's saying if you need to figure out the antiderivative of natural log of x, which we do, you can figure it out using integration by parts. Oh, right, integration by parts. I remember that from a little while ago. We had this formula that said the integral of u dv is equal to uv minus the integral of v du. So what I was supposed to do is look at this thing and figure out what should be playing the role of u and what should be playing the role of dv. So in this case, what we did is we let u be equal to the natural log of x, and then all that's left for dv is this dx over here. And if u is equal to the natural log of x, then du is 1 over x dx, because du over dx is 1 over x. And v must be equal to x because the derivative of v, dv, would leave you with just this dx over here. So now I can figure out the antiderivative of natural log of x. I guess I could write that out. The antiderivative of natural log of x dx is equal to, using integration by parts, u times v, so x natural log of x, minus the integral of v du, so x times 1 over x, those cancel out, and I'm left with just 1 dx. And since the antiderivative of 1 here is just equal to my variable, x in this case, I get x natural log of x minus x, and then I guess you could put on a plus c here. Although since we're going to be using this for a definite integral, we won't even end up needing this plus c. At any rate, this work on the side here will help us figure this out, because the step I'm at over here is figuring out the antiderivative of the natural log of x so that I can evaluate it from a to e. And the antiderivative of the natural log of x is what I wrote over here, maybe in red, x natural log of x minus x, and I don't have to write the plus c because we're going to evaluate this at its two different endpoints, so the c would just cancel out. So what I get is that this is equal to the limit as a approaches 0 from the positive side of this expression. And this is easy enough to deal with. To evaluate something from a to e, just change all the x's into e's, then change all the x's into a's. When I change all the x's into e's, I get e times the natural log of e, but the natural log of e is just 1. So I get e times 1 minus e. Looks like that's going to cancel out really nicely for me. And then when I go changing all the x's into a's, I get a natural log of a minus a. So if I clean this up a little bit, this is 0. I could take this negative and distribute it to these two terms. So the negative of a negative a would just leave me with a positive a, and the negative of a natural log of a, I could do minus a natural log of a, and I could try to evaluate this limit. Well, the limit as a approaches 0 from the positive side of the a is just going to be 0. So this limit is just the same as the limit as a approaches 0 from the positive side of negative a natural log of a. And unfortunately, that's not a limit you can just look at and figure out. It's an indeterminate form, but maybe, I don't know, you remember way back in 4.5 when we learned how to take limits of indeterminate forms. You have to use this thing called L'Hopital's rule. To use L'Hopital's rule, you got to first write this so that it's in the form that you need for L'Hopital's rule, namely a fraction. And the way I can do that is, instead of a times the natural log of a here, I can make this a to the negative 1 power if I put it down in the denominator. So this expression is equal to this expression. And now I can use L'Hopital's rule. I have an infinity over infinity case. So L'Hopital's rule tells me that this limit up here is the same as the limit of the quotient of the derivative of the top and the bottom. In other words, take the derivative of the natural log of a, so that's negative 1 over a, when I count for the negative that's up here, and then take the derivative of a to the negative 1 power, well, that'd be negative a to the negative 2 power, or negative 1 over a squared, if you want to write it in that format. And this I can clean up a little bit. This is just the limit as a approaches 0 from the positive side of, let's see, if I multiply by the reciprocal of the denominator, I think the negatives will cancel each other out, and I'll get a squared over a, which reduces to just a, and the limit as a approaches 0 from the positive side of a is just equal to 0. And you're like, 0? How can that possibly be the case? Well, what we're doing here is we're determining the area of the natural log of x curve, which looks like this, loosely speaking, up until e. So what happens with the natural log of x curve is it crosses the x-axis at 1 here, because the natural log of 1 is equal to 0. So when I'm looking at the area underneath this curve, I'm kind of looking at all this negative stuff and then all this positive stuff. And it just so happens that things work out perfectly so that this negative area cancels with this positive area, and I'm left with exactly 0 as my answer. Next question, determine the area bounded by y equals the square root of x and y equals x over 4. You don't need a graph for this guy, but if you want a graph, you can sketch one. If it helps to have this for reference, this, loosely speaking, is what's going on here. We want to figure out this area right here. Well, to figure out this area right here, we need to know our bounds of integration. In this first one, we're supposed to integrate with respect to x. So we'll have to figure out the bounds of the x values in this picture. Well, let's see. This one is pretty apparent. It's just 0. But what about this one up here? What if I can't tell what that's equal to? Well, all I got to do is take these two equations and set them equal to each other. Since I want to know the x values of the points of intersection, I want them both solved for y. How convenient they already are. And then set those y's equal to each other, and that leaves me with an equation that only involves numbers in the letter x. So I can solve this pretty easily. Let's see, squaring both sides, I'd get x squared over 16 is equal to x. So if I subtract x from both sides of the equation, I get x squared over 16 minus x equals 0. And I can now factor out an x from each of those, and I'd be left with x over 16 minus 1 equals 0. So this is telling me that either x equals 0 or x over 16 minus 1 equals 0, in which case x over 16 equals 0, in which case x is equal to 16. Oh yeah, that makes sense, because if x is 16, the square root of 16 is 4, and 16 divided by 4 is also 4, so they would have the same heights here, so it would intersect. Anyways, my bounds of integration go from 0 to 16. And then what do I want to integrate? Well, it's just the top curve minus the bottom curve. In this bounded region, the square root of x is the top curve, so maybe I'll write that as x to the 1/2 power, looking ahead to when I have to take antiderivatives. And then I want to subtract the bottom curve, which is x over 4. Maybe I'll write that as 1/4 x, again, to try to make my antiderivative life easy. If we could figure out this definite integral, we'd be done with the problem. See, I think we can do that, because the antiderivative here would be 2/3 x to the 3/2 power if I add 1 to the exponent and then kind of bring the reciprocal down in front. And then the antiderivative here, well, I'm going to have x squared, but I need a 1/2 out in front, and that 1/2 and this 1/4 will give me 1/8, and it's still negative like it was above. And I got to evaluate this thing from 0 to 16. Plugging in zeros, that's going to be awesome. Plugging in 16s, yeah, not so much. Let's see, I would get 2/3 times 16 to the 3/2 power, and if you know that, great, and if you don't, pull out a calculator, minus 1/8 16 squared. And maybe just for the sake of showing my work, I'll do minus 0 to really demonstrate what happens when you plug zeros in here. Let's see, 16 to the 3/2, this 2 means take the square root, so now it's a 4, and 4 cubed. 4 times 4 is 16, times 4 again, I think ends up giving me 64 here. And then 1/8 of 16 squared, well, one of those two 16s times the 1/8 just leaves me with 2, and 2 times the 16 leaves me with 32. So it looks like what I get for my final answer is just 128 thirds minus 32. And I guess I shouldn't call that a final answer, because I'm going to take it a step further and get a common denominator. 32, if I need the same denominator as 3, is equal to 96 thirds. And 128 minus 96 leaves me with, what, 32 thirds? So I believe this area in question is 32 thirds. The nice thing is we can kind of confirm that by doing this problem again, but now integrating with respect to y. So if I'm integrating with respect to y, it's not the x coordinates of the points of intersection that I'm interested in, it's the y coordinates of the points of intersection that I'm interested in. And you can either just look at this and be like, well, this is when x equals 16, and when x equals 16, the y coordinate is 4 in both of these two equations, so it must go from 0 to 4. But in case you didn't think to do it that way, you could also solve these two equations for x. So for the first equation, if I multiply both sides of the equation by 4, I get x equals 4y. And for the second equation, if I square both sides, I get x equals y squared. And then I could take these two equations and set them equal to each other. 4y equals y squared is the same as y squared minus 4y equals 0. And now if I factor out a y, I'm left with y minus 4 equals 0. So either y equals 0 or y minus 4 equals 0, in which case y equals 4. So these will end up being my bounds of integration when I integrate with respect to y, which is what I'm supposed to do here. If I'm integrating with respect to y, the way to think about this is it's the right curve minus the left curve, not the top curve minus the bottom curve. So the right curve is this linear one, and this linear one is the one I solved to be equal to 4y. So I want 4y to go first, and then from that I want to subtract y squared. And I think this one's going to work out a little bit nicer than the first part. I did that on purpose. I kind of wanted, when you integrate with respect to y, which is generally the more confusing case, the numbers to at least work out nicely for you. So the antiderivative of 4y is 2y squared, and the antiderivative of y squared is 1/3 y cubed, and that needs to be evaluated from 0 to 4. If I go plugging in 4s, I get 2 times 4 squared minus 1/3 times 4 cubed. And if I plug in zeros, I just get 0. Some unnecessary parentheses there just to try to show my work. So what do I have here? Let's see, 4 squared is 16, and 2 times 16 is 32. And then 4 cubed, 4 times 4 is 16, and 16 times 4 is 64. So I get 64 thirds here. And hopefully 32 minus 64 thirds is the same as 32 thirds. It is, but let me show you how. 32, if I need this common denominator, again, I can write that as 96 thirds. And 96 thirds minus 64 thirds is just equal to 32 thirds, which I feel pretty good about, or hopefully you will if you got to that point, because that checks out with our answer that we got up here. That's the end of this quiz.